Last thing that we're going to look at is concept called models, right? We are going to look at models, right? So all we've been saying all along is that, well, predicates have got no true value. If we want to use natural reduction rules on predicates, we have to pick an arbitrary constant. So that's all we've been saying, or that's something that you could have deduced from what we've been saying. We see that if we have got all x px implies qx, for example, we are saying that this is not a really good you cannot say whether this is true or false up until you know what x refers to, right? What set x refers to, and what p refers to, and what q refers to, right? So this is what we call a model. So a model consists of a universal set, then relations within the universal set. Right. So now we then say, what are we talking about? And what are the relations that we have? So if we want to look at this, we can now come and see task world, which has been a model that we've been dealing with so far. So a task world, we know what the universal set contains. It contains of a board, it contains of sides, left, right, center, and so forth, and elements inside the task world. So that is a world or a model which we can practice this on. So we have something like this: says draw a task world serving as a counterexample to show that there's no proof of the argument. So if you want to show that there's no proof, or to show that it is not valid, you want to draw a world where this is true, but this is false, right? You want to draw a world where the premises are true, but the conclusion is false. So you just draw a task world, something like this, right? Put some rows in and some columns. And remember the notation of the task world: this is back, this is front. You can label it on your, you can label it on your yours. So this is front, and for me this is left, and this is right. Okay, so it says all objects that are in the same row and are not equal, right? It means that x is a cube and y is a cube. So only this statement says only those objects or the objects that are in the same row, right, are cubes. Cubes can only be in the same row. Cubes can only be in the same row, right? So this would say if we have a cube and if we have a cube, then that's fine. But if I have a cube and I've got a dodecahedron, then that's not fine. So if we have something that is true in the same row, then we have that. Then this one says x is a cube, y is a cube, therefore x is in the same row as y. So it says all cubes are in the same row. So if we were to have, say, an object A that is a cube and is of medium size, and an object B that is a cube and is large, for example, right? Does it satisfy the first condition? All objects in the same row, nothing is in the same row, so false implies anything is true, right? So this is true there. But then it says, find me two cubes. I find you two cubes. They should be in the same row. No, they're not in the same row. Therefore, this is a potential model that can pass or serve as a counterexample to show that no proof is possible. Right. So this is the same one from different papers. Interesting. Then let's look at something like this. It says, consider the task world below. The world illustrates that this is not a logical consequence of this premise, right? explain why this is the case. Explain why this is the case. So this is a tetrahedron. So this is a tet. This is a cube, right? So this says not some x tet x. Remember, we said not ex is equivalent to ax not whatever we were looking at. So in this case, we can transcribe this to say O x not tet x. So we're talking about all objects that are not tetrahedrons. Right? So the conclusion is that all objects are not tetrahedrons on the task world, but we have got tetrahedrons. So this is false, right? But then let's see, does it satisfy the first two? It says x is to the left of y, then x is larger than y, right? So over here we've got back, we've got front, we've got left, we've got right. So it says every object that's on the left, or all objects on the left are larger than their counterparts on the right, right? But here we don't have an object that is to the left of the other. So this is false, and true or false, this is going to be true. And here we're saying if y is smaller than x, all objects smaller than x, it means x is a cube and y is a dodecahedron, right? So, but here they gave us the indication that they are all the same size. That's why they gave us a 3D. So we have got, this is false, none of them are smaller than the other. Then we've got a cube and a dodecahedron, right? So it means that this is also true. But all objects are not tetrahedrons. This is false because we can have tetrahedrons in it. So that is the argument we want to give. So we say first premise is true. First premise is true since why is the first premise true? The first premise is true since no object is to the left of any other object. To the left of another object. Right. And the second premise we have equal objects, same size objects, therefore it is also true. Objects, therefore it is also true. The conclusion, however, says the conclusion says, what does the conclusion say? All objects in the task world are not tetrahedrons. Are not tetrahedrons. All objects in the world are not tetrahedrons, whereas we see two, whereas they are two in the given task world. There are two in the task world. All right. So that is what we do. All right, so that's our short video on models, and it speaks to you generating a task world model that makes something true and something false, or interpreting the given.